Hey folks, Assalamu alaikum. I'm Mohammed Shari Al So welcome back again. So this is our another video on mathematics for machine learning series. So it's part of ML Summer School obviously, and today we'll learn the application of differentiation, integration, and probability in machine learning. Although we are not going to cover all of the topics, all of the things in depth, but the basic things which you need to know about these topics for machine learning. Okay, so here if you look into this, if you just look into here, you can see if we assume this as y-axis and this is an x-axis. Here in x-axis you can see time, and y-axis we have distance, right? So the thing is, we can see a plot here, or you can see here. So in the plot, what you can see is basically there's a graph, and from the graph, what do we understand as a whole? That's a point. What these graph actually tells us. So we'll learn about that. So first of all, this is basically if you just look into that, in each of the point, in each point basically in the graph, if you create a linear line, you do get some points. What are these? So specifically, if you just look into here, what this line means is the vehicle. If there is a vehicle and within particular time, for example, maybe here for just referencing, okay, for this point, assuming that this is t equal 3 seconds, for example, and for this if it is t equals 7 seconds, okay, if this graph refers to this. So what this means is that in this particular time range between 3 to 7 seconds, we can see there was actually no distance covered, right? You can see because the distance is same. In 3 seconds, assume that the distance d equal was 5 minutes, and in 7 it is still the same. That means the distance is what it was. That means again we do know something like that, which is S equal Vt, right? From the Newtonian mechanics, we do know some sort of law about it, like okay. So although it's not distance, but we'll learn about these things, but I'm just referring as d, v as what you call it, some sort of speed or whatever, and t as time, right? So from here we can see v equal s by t, right? So again we have learned y equal mx, right? So if we want to look for m, which is y by x, right, which again means for this one v equal s by t. So s refers to whatever, for distance we may call it s, no issues with that. So it refers to the y-axis value, t refers to the x-axis value. That means the v, the plot we have in general basically refers to some sort of actually the speed, okay, great. Now the thing is, if you just look into here, we can explain more. So these points actually refer to the initial acceleration away from vehicle's origin, okay? So once a vehicle or a car something starts, these points, basically this graph basically refers to that one, the initial acceleration. And now the thing is, after that vehicle is stationary, which means okay, the vehicle has stopped for a while, and then again there is some sort of linear line, almost a linear line, not a linear properly, we can call it something. If we just create a line, you can see the vehicle traveling at constant speed. Now why is it constant? Because as m equal to y by x, and now if we have some sort of y by x, and if we have m, which is like obviously y by x, like, and if it is fixed something like that, obviously we'll have a linear line. So this line, almost a line, although it seems to be like some sort of curvy, but it's almost a line if you just plot it properly. So it refers to a constant speed, because when you fix the m, then the line actually looks like that. So we are actually continuously relating this graph with the linear algebra we have learned previously. Okay, great, no issues. Now again, the thing is, what do we learn from it? The thing is, distance by t. If we look into here, you can see the derivative is the slope of the line. So the derivative we do get here actually is the slope of the line. So okay, we'll learn about this. Let me just go here. That's an interesting factor, and we'll see right now. Okay, so assume that for example here, when we have distance by time, as I mentioned earlier, s equal vt, we are considering if we just keep distance as s, then s by t is v, right? So that means the graph we have, and if we just want to find the actually the value or the points or the plot basically for this graph, we can get v, velocity or speed, whatever you call it. So for, we can call it speed here. Okay, let me just give it v instead of s. Okay, great, no problem with that. So you can see slope m equal change in d, change in t. That means no issues, same thing. So you can call it del s by del t. You can call it call this as well, no problem with that. Okay, so here in this line, if you just look into this graph, basically we have some line. You can see this is a linear line. So actually there was a graph, right? So our goal was to actually some sort of our goal was to check the graph properly using some sort of line. So when we started creating a line, we saw, okay, in this graph, this line seems to be very close to the graph. So we can call these graphs m equal 0, or you can call velocity equal 0. When you see this graph and we plotted this line, we saw like, okay, when the value of m is 1, this actually graph actually looks similar as the plot green one. Okay, so that means this line refers to m equal 1. Again, there is for these points we can find multiple actually lines which for m equal 1, half, and whatever it is. Now this is not the point. The point is different. That is, here this graph or the plot as a whole or the line refers to some sort of actually the slope. Now here, if we just take it to this point, now what happens here? Okay, now we are getting some sort of velocity, right? If we plot velocity in y-axis and time in x-axis, what happens? Interestingly, this is what happens. If we get we basically get some sort of graph, right? Now if we want to find its slope for these particular lines, you can get for this particular line from here to here, m is equal 1. For this particular graph, from here to here we are getting m equal to 2. For a particular point from here to maybe here, we're getting m equal to -2, and so on and so forth. So earlier in our linear algebra 1 parts, we did learn like, okay, the y equal to mx plus c and others, right? So what was the c? C was basically how much required from the y-axis and then the plot. This is how things do work. This part is c, and the plot for this line is basically, if we just get this, m equal del y del x, right? This is how things do work. Okay, this is how we do get the thing. So for a particular graph, we can use this line basically to get its plot. So for particular graph, so here from here to here, we wanted to get its plot, so we got it. It was equal to 1, right? Okay, So yeah, we just learned about, like, from the graph we can just get a slope, and from here we do get some values. These values, interestingly, for this graph, when in y-axis we have v, in x-axis we have time, we this graph, or sorry, we say this slope basically refers to acceleration, which we get by a. We call it sometimes you will see we refer to this by a. No problem with that. So this kind of things are part of differentiation. Okay, we will see that something like you will see dx by dt equal m or something like that. Okay, so we have this kind of format, or we have just seen y by dy by dt as a speed, you can call it, so something like that. So these are differentiations, we will see that. And study of areas, basically we'll learn about this. In general, the study of areas or curve, basically under curves, are related to our integration. Okay, so if we have this graph, and if we somehow want to know the area that this curve covers, so we'll have to use integration. Okay, now let's talk about this one. For example, here in the polygon, what can we see? So we can see this polygon can be divided into multiple parts. Here we can call it we can get a rectangle, and here is we can get a triangle. So using that we can get the area, right? So this can be one of the formats, but interestingly, using integration you can just easily get that. Okay, and for example, again, if we have this one, like if we have a circle, and if we want to get the area of the circle using some sort of square, like for example, if you create a square, how much can we cover? We can just cover this line, and these parts will not be covered, right? Interestingly, if we just have 4 lines here. Okay, if we increase the lines, you can see 1 2 3 4 5 6. When we have 6 lines to cover this circle, you can see, okay, it covered much more area than before. And here, if we increase it much more, then we can see it almost covered the whole circle. But again, if we have much more than this number of lines we have, maybe 100, then you can see these almost cover the circle. That means if the lines are very small, it will actually cover the whole circle. So this is again goes within our integration. Okay, great. So this is how we will just talk about those in the integration. Now let's talk about the differentiations as a whole, where it is applied and so on. Okay, so differentiations or differentials. Okay, so it basically optimized by finding minima and maxima of curves. Interesting. What is that? That's the point, right? What is that? Okay, so just understand by this here, there is some sort of graph, right? This graph. So in a particular point where this tortoise is standing, we can get its slope. Now the thing is, okay, maybe m equal to, maybe it will be some sort of positive, obviously 2 or something, no issues. When now in this point, we'll see that, okay, what's the value of m? It might be 5 or something, assuming that it's positive. Obviously it's going in this way. If it was in this way, we would have considered it's in negative. Now here in this point, when we get the slope, we can get what it is we will get m equals 0. Now earlier you have again seen this kind of things right here, right? If in this point, so m equal to 0. So what's the need? What's the point of going here? If you have learned differentiation earlier, so the value or the main concept of getting minima and maxima is very important out here, because sometimes our goal is to know the maximum value we can get, okay, or to know the minimum value we can get, okay, sometimes something like that. So using differentiation, you can see that, as I mentioned earlier, like some sort of, we can call m equal to, for this dc by dc by dp, okay, something like that. In this point we will get m equal 0, okay, something like that, because you can see they are not changing, right? In this point the value of dc won't change, right? That means 0 by some sort of value, maybe 2, 3, whatever, because maybe here it was 2, here it was 5, so 5 minus 2 is 3, so you can call it 3, no problem, 0 by 3. Okay, we'll get obviously 0, no problem with that. Now this refers to the minima, okay. Now we will learn why it is important, obviously, and let's just look into this example. I believe I have just used this multiple times. We'll just remove that. Now let's look into here. So in our coding examples, now I have provided this link here as well, and I will obviously share this in the description section. If we just look into the code, you will see that when we run a code, what happens? Our main goal is to reduce the cost function. We will later learn what the cost function is or how we reduce that. Surely we'll learn that, okay. We will learn two type of cost functions, not like in depth how it works, but the thing is cost function, we'll learn about that. So our goal is, in some sort of way, we do get some sort of thing called cost, okay. So our goal is to minimize it. Now you can see that here it was m equal to 2, here it is m equal to 5, here it is I'm not sure, I've just provided some random value. Here it is m equal to 0. Obviously it will be m equal to 0, there is no problem with that. That means from here our goal was, like you can see what we were doing from here. I believe it should be much more mid, okay. Yeah, it should be something like 4, it should be something 2 or something, okay. I've just provided random one earlier, but yeah, this should be something like that. Now what our goal is to, like, from m equal to 4, as we know what's the value, m equal to dc by dt, our goal is to reduce that. So from here we are moving to the points, and we're looking for some sort of point where m equal to 0. So we are going here, you can see from here we just have reached here, and you can see its values 2. So from there we have just reached another point which is m equal to 0. So that's our goal, but in general it doesn't happen, to be honest. M equal to 0 or something, or cost equal to 0, it doesn't happen, but it's a theory, like we're just looking for that. So how do we go for that? We do use this gradient descent, okay, which is called gradient descent. So we are basically descending using gradient, and this is how it is. So something you will learn, gradient descent. So you can see from here in coding, when you run a machine learning code, you will see the cost is reducing. Here you can see 0.541 from here, and when the epoch, that means the whole code is run 20 times here, okay, epoch 1 to 20, that means 20 times. After that we were using gradient descent, and we were looking for the least value or the minima, basically. So we got a point where the cost is very less, which is 0.024, which is very less than 0.541, right? So it has decreased. So this is the uses of gradient descent or differentiation in our coding. At the same time, in reinforcement learning, learning, which we call something like RL, okay, you can see the goal is different. The goal is totally opposite. The goal is to reach the maximum point. So it was basically, here we were looking for minima, but here we're looking for maximum. Why? As you can, okay, now the point is, what is reinforcement learning? So what reinforcement learning is, basically you have a robot, okay, or maybe a car, okay, something like that, okay. So a person will actually set a road, okay, something like a road, okay, and there will be a finishing, obviously, here, okay. Assume there is a finishing point, okay, this is finish. So you have to provide a code to the robot or the car so that it follows the line, and it can again go and finish the actually path as soon as possible. So in this way, so how we solve the problem is, we call it reinforcement learning. So we do basically set something like, okay, maybe assume that there is some sort of line here and is the middle line. Okay, I'm just drawing rubbish things. Okay, sorry for that. Okay, assume that just it's just curvy lines. Okay, so this car is basically, the car is supposed to go can go from here, here and here. Okay, so there might be some sort of rules that if the car goes from this part, this is the road, okay, and this is outside the road. If the car crosses the road and goes from here, there will be some sort of penalty. Okay, so there is something, if you learn AI, what you will learn is basically you can create a function which will understand if this car is getting penalty, and if it gets some penalty, it will take some action and get back again to the main road. So the main goal remains is, in general, what player does is to follow this central line. Okay, to follow the central line. Sometimes so the model sometimes doesn't work well, and it goes from basically it goes to this road maybe, and then it learns, hey, I'm getting some penalty, -1, -2 or something. So it learns and it comes back and again follow the same line. Okay, this is how this reinforcement learning things work. And AWS has some awesome reinforcement learning gaming. So okay, there are a lot of things we can learn, to be honest, in later on. But the thing is, in this process, when you follow the central line, okay, this might be a goal, the coder can set a goal. Okay, if you follow the central line and if you go through some sort of milestones, you can set some sort of scores as well. So the goal is to get maximum score, right? So assume we have a score 70, and at that point what happened, it just got out of the road and it went here. Then the score will be -1. It will be added to like 70 -1, then -2, etc, etc. Then it will learn, hey, the score is getting decreased, so it is 67, so I have to get back to the main road again. So it learns and it get back to the main road. So the goal remains to increase the score. So if it follows the main road, main line for much more time, then it increases, right? So here you can see, for reinforcement learning code, the goal remains to get the maximum score. Sometimes you see it is 99 and then 199, then 68, 199. That means it's failing to learn, or it is getting out of the road, and then it comes back again, and the maximum score, assume that it is 200 for this code and or example, then it is doing good. Okay, this is the maximum score, and then it is going in the right path. These lines means that this is going the right path. Then again it makes a mistake and we are penalized for that. Okay, 199 minus some sort of what, 149, right? Something like that. So penalized for 149 points, so something like that. Then it learns and get 1079, then it again fails and goes for 37. So this is how things work. So if you haven't learned reinforcement learning by now, you will, I believe. We will have these videos sooner. Okay, now again talking about that, we can learn that, and in integral, talking about the integration or integrals. So one of the things we learn about this is basically the line. Okay, so we will learn about this, like we will need to know the area covered here. Okay, so we will use integration for that. Okay, so yeah, let's get started. I believe to learn much more about differentiation right now. Okay, now let's get in. So assume that this is a line, sorry, this is not a line, this is a graph provided here. Okay, and maybe this is a point, no problem with that, and this is a point, no problem with that. So here what is mentioned is, what is the limit as x approaches 5 in the expression x square plus 2x plus 2. Okay, so this is the graph for x square plus 2x plus 2, no problem with that. So the goal is to, what is the limit as x approaches 5? What does it mean? Okay, what does it mean? It means was the value of y when x approaches 5. Okay. So here you can see this is our 5, right? 5. So the goal is to know the value of y. So from here, in general, from the plot, if we can see, maybe it's very near to 40. Okay, very near to 40, but we don't know exactly what it is. There is something like this which we can do here. So if we have x squared plus 2x plus 2, what I can do is x approaches 5. Okay, very near that. So x approaches that means very near to 5. So when x approaches to 5, when we are provided that, we can just add this value, like for x we'll just do that. 5 squared 2 into 5 plus 2, what we get is 37. So this point, that means 5, it is 37. So we can do that basically. So it is easy, right? We can just implement this value instead of x, right? We have got the value, but there is some problem. That is, in mathematics we can't do certain things, which is we cannot divide something by 0. Although we can divide 0 by something, which we get as a whole 0, no problem with that, but we cannot do this thing. We can't simply. So if we have been provided this line like x square minus 1 by x minus 1, this is the actually graph or line, whatever you said. If we have this line for this equation, and someone says if x approaches 1, what should be the value of this one, or something like that. So if you now easily actually replace 1 here and 1 here, at the start you will see like, okay, 1 minus 1 is 0. So whatever is here, no problem with that, to assume that we have something here, but in this part we'll have 0, so which is not possible, right? So there are some process, obviously. So how we do it is basically we'll divide. We know we have a law which is a square minus b square. Using that, we have like a square minus b square, we get a plus b minus a minus b. So using this from here, we can get x minus 1 plus x plus 1. So just divide these things, x minus 1, x minus 1, we just cut them out, and then we have just x plus 1 here, right? They are both actually the same. Now the thing is, then now as now we don't have something like in here, like if we just now we can use x equal 1 instead of this function. So here x equal 1, and you can get it's 1 plus 1 is 2. So here again from this graph you can see, if when x was 1, the value of y was 2. So it is done. Okay, now let's talk about the derivative notion. Okay, so how do we represent differentiation? So for some sort of equation which is y equal fx, whatever you call it, fx basically means some sort of function which has x as variable, whatever we call it. So for example, fx can be x square plus 2x whatever plus 3, no problem with that, we can have that. Okay, although these might not look good here. Okay, now it looks good. Okay, the differentiation operator which we do refer is by d by dx. Okay, d by dx, or this one. Okay, now there are lots of things which is something. First of all, the thing is called first derivative. Okay, what is first derivative? So remember, we had this one, distance by time, and from here maybe we had some sort of graph or something like that, obviously, and we got some sort of actually slopes here as well. Let me just give it a lot of points, obviously there are lots of slope we can get, and here we'll obviously here we will have that almost same something. There are a lot of things we can get. So here this m was basically what, d by t, or changes of d in y-axis by changes of t, obviously, right? We can call that. Okay, but again this is basically first derivative. Okay, Now, why are we saying that? We'll learn about it. Now, this m was basically referring to some sort of velocity, right? Again, the acceleration was what? It was again the differentiation of the same thing. Of the same thing. How can we say that? Okay, that's interesting. So, for example, if we just use this, we have now m, right, or v, right? A was dv by dt, or changes of this d and this d. What this d refers? So d is basically dv and del d is same. Okay. It might be. Okay, let me just clear that. Okay, del, for example, just understand that del x, what does it refer to? Let me just show you. Assume that we have x equal what? 2, and we have x equal 3. Okay, the change in x-axis now we have is, we call it del x, which is 3 minus 2. Okay, we can again call this del x as dx. This d does not refer to distance. Okay, we can call that dx. In differentiation we do use d. Okay, now this d is different as it was for the distance, but yeah, that's why we can use s for here. It becomes easier. Okay, now for acceleration, understand that for the acceleration we are getting the graph was some sort of what we had as velocity by time, right? So the change in velocity by change in time, right? Interestingly, now if you use this the value of v here, like you see v equal to del s by del t, if you just remove that and we provide del s by del t, what happens? Let me just remove these things, and things should be pretty much easier for you right now. Let me just remove these things. Here you see we have used or as del s and del t is referred to as this. Let me just do this. Del s by del or ds by dt, whatever you call it. Okay, it is basically referred to the changes, small changes we do. The del del x is equal to dx. Okay, something like this. So it just refers to the same thing, the changes in x. Okay, changes is x is referred to del and dx is the same. So now you can see we have applied d by dt. If you just look into here, d or d by dx, whatever. Okay, so if we just look into this thing, it is applied here 2 times, right? D by dt on s. Okay, interesting, right? Okay, on s we have used it 2 times, so it is second derivative. Okay, a to get a we have used or differentiated s 2 times. Okay, so this is how things do happen. So now tx, whatever the problem is or whatever it is, now as we have seen the x-axis, we had actually t, right? So that's why it is t. Okay, and y-axis we had whatever, we had s, we had a, whatever it is. So this is how things do work. So we can refer to, like for example, now the thing is if we make things easier and refer to like this, let me just show you again. Okay, let me just remove these, and let's talk about this one. Okay, assume we have s by t. Okay, now what v is, what do we call v? How do we get v? We know, or we get it by del s by del t. We can call it what? ds by dt, right? Again, this v, right? Obviously, great. So we can again call this ds by dt as s, something like that. So this is how we can see y dot y something. We can refer to this, or we can call it like that. A lot of options actually depends on that. So if we had a function, we could have called it something like that. So this is how we represent that. We can represent it by this, we can represent it by this, and a lot of options we do have. Okay, and the second derivative which we had, a equal del v by d, as we know, we can already use d rather than del. We will use that. Okay, dv by dt, right? So yeah, that is what we can do. So we can call it again for the here v, as we have talked earlier. This we can put the value of v here, so it can be written as d dt by ds dt. So this thing is, we can refer to is something like, here you can see d square, we have 2d, right? D square, and you can see dt dt, right? So instead of d square t square, we will write dt square, and we'll have s. This is how we refer to this, or we can call it s here, something like that. Okay, there are a lot of things we do have. So these are the symbols to represent, okay, how many times we have used differentiation here. That's it, simple as that. So nothing to worry about. Okay, there are some differentiation laws we will learn right now. Okay, so the laws are simple. So let's learn this one. So if we have some sort of constant value, okay, and if we want to get its differentiation, which is d by dx, okay, then we will get the value or the answer as 0. Okay, so we can actually understand that in general. For example, if we had the example right earlier, something like graph, then it was something like that. So if we just look into this here, the slope here, so for the point here, like for x equal to 2 and x equal to maybe 5, okay, and the value in y was maybe 3. So here you can see the slope m equals what? We have the del, or whatever you call it, you can use, right? Okay, I'll use both del y. I'm just mixing that up. Okay, del y, it should be y, right? Okay, y by del x or dy by dx, whatever you call it. You see the value is 3 and it is 3, right? It is not increasing. That means we'll call 3 minus 3 by, what is the change in x? It is 5 minus 2, which is what? 0 by 3, which is 0, right? That means now I am talking about it. That means if you just look into here, what we can do, as we have said, that we can just write it like d dx y, and you can see that y is 3, right? In this line y is 3, it is not changing. That means when we have some sort of constant out here and we are trying to get its d by dx, now this x, what is this x referred to? This x refers to the changes in this axis, which is x actually. That's why it is d dx. If it was t axis, then it would have been t. Okay, that is it. It is not something. We're just trying to find its change, okay, or slope, whatever you call it. Here is the change in this axis, so we just put it here, and the d, and this, then the whatever we have, function or constant. So as the value of y is 3 here, it is not changing. You can just use 3 here, and you can easily understand here, that is if the constant or if the value is not changing, we can just call it 0, because you have seen that with example. Okay, let it be. Now for other laws, we are not going to look into the examples from scratch, but these are the laws you have to practice and memorize. Although these are not going to be implemented directly in machine learning, but these are the differentiation laws. So if you want to get d by dx for x to the power n function, we do get something like n, then multiplied by x to the power n minus 1. So for example, if we have this function ddx of like x to the power 4, what do we get? As mentioned, 4 is n here, so 4 will be here, then x obviously n minus 1, that means 4 minus 1, which is 4x to the power 3. That's it. Same goes for this. So we have another law, which is some sort of constant multiplied by some sort of function. So if a constant is multiplied with a function, what we do is we somehow take this constant here. We don't actually use the differentiation right now for this constant, okay, just like that, not like that, okay. Here we had to do the differentiation on the constant, so it was 0, but this time this constant will come up here and it will be multiplied with this. You see, now the differentiation is done only on the y. So then c dy by dx, that's it, okay. That means this c actually came here before the dy by dx, that's it. So example can be seen here. If y equal to x to the power 4, so what we can do is we can easily understand that dy by dx is 4, x to the power 3, we got it from here, right? Now somehow if someone say like, okay, do the differentiation again, what will happen? If someone say do the differentiation again on this 4x3, what will happen? So if we just differentiate with 4x3, what will happen is this 4 will come up on top, and then we will have dx x to the power 3, and we will apply the differentiation on this, just like that, okay. And one of the examples are here, d by dx, and we have 2y, so this 2 is constant, so it will come on top, okay, just like that it came here. So then we just followed for this, that's it. This is how we can do this. There are a lot of things, okay. Then what? So then y equal to 2 x to the power 4. For this again we can follow a lot of things. So here you can see that if we have y equal to x to the power 4, so if we have the differentiation on y, what we get is 2 is constant, so it will be in the top here, no problem. Then we solve the do it for x to the power 4, and we have seen it earlier. If we have x to the power 4, we get the differentiation value as 4x3, x to the power 3, okay. So I've got it. So then what we're done, then we can just multiply this constant, no problem. Then great. There is another one, which is this one, which is we can have d dx of y plus w, something like that. Two functions or variables or whatever you call it, we can have them in addition format. Then what you can do is we can write it like dy by dx plus dw by dx, the basic mathematic principle. For example, if y is equal to x to the power 4 and w is equal to x to the power 9, if you just want to follow that, obviously, then we'll just do it for individually and then done. That's it, simple as that. I believe most of you do know differentiation much more in depth. So yeah, that's the basic one. Now these are some sort of examples for you, and you can just do the exercise, and we will share the solutions within a week in our Discord channel. Great. Now you can again follow another example, which is here. If we have this format, okay, so wz, whatever it is, so what it is, assume that we have two functions and they are, or variables, and they are actually in multiplied version. Maybe you might have learned it by uv ddx of ub or something like that. You might have learned it like that. So we call it u dv dx plus then what, then v d vu dx. That means, okay, once we will consider one of the variables as constant. For example, here we have thought u as constant, and then we've done differentiation on this, only the v. And here we have considered u as constant, and we have done the differentiation only on u. That's it. So there are a lot of laws, to be honest. These are the things I believe you have learned earlier, or you can learn that. And there is another one which is d by dx and u by v, which we call, maybe sometimes you can see like that, u by v, okay. So we have just used w by z. So the law is simple. This is how we do it. If you have this like that, we just use v and then du by dx minus, and then we do what? U dv by dx, then v square. Okay, so these are some sort of laws, and you have to learn them and you have to apply them. Now, to be honest, in machine learning, or these are not something you need to apply, but for mathematics you need to know how these problems are solved, because these are the formats in which the problem will be some sort of equations, others will be there, and we have to apply ddx, but we will not apply or we will not calculate them. In general, there are already libraries which will calculate those for us, so we don't actually need to know how to solve this problem, but it's important as a science student. If you are from science, you need to know how to solve the problem, but not directly for the machine learning purpose. Okay, now for the chain rule, which is very, very important for us. Okay, so the chain rule is, for example, if we have this one, ddx of y, how we can write this thing as this? We can write this thing as dy by du and du by dx. Aren't they same? Yes, we can just remove them, right? And this is still dy by dx, but still if we don't remove them, we can see there are two differentiation we do have right now. One is d by du of y, another is d by dx of u, which we call is ddu. Okay, ddx, as we call is ddx, we can call as ddu. Okay, so something like that. But when is this important? Now, as these dx or something, you might have learned or memorized that in your school, college, whatever it is. In general, we do have x and y axis, so the most of the problems are in general in dx or dy, whatever it is. But in real life, there will be much more axes. Okay, so sometimes we have to divide the problem into different axes so that we can solve it easier. Okay, so here you can see this ddx was used, here you can see ddu was used. So yeah, and y and u are the variables right now, and these variables are something we have to understand. So assume this is our problem, y equal to 2x square plus 8 whole square. Now in general, we haven't learned any law for that, but we did, to be honest. How? Assume that these whole part is considered as u. Assume that. Okay, if we consider the whole part as u, okay, u, then what does it become? It becomes u square. We have learned something for ddx of something like x to the power n, haven't we? And right, so for the power rule, basically for the power, something like that, we have learned something like that, right? Interestingly, once we created like u square or something like that, great, there's no problem. Now you can again see some interesting factor, that is, when these things did match, then we were able to solve the problem. When dx of x to the power n, they were same, then we were able to get n x to the power n minus 1. But if y equal to u square, then okay, no problem. And basically y equal to x to the power n. Okay, no problem. So if we have this and we have ddx of u square, how are we going to solve the problem? We can't, right? So that is the reason we can divide this problem into two parts. We're just learning mathematics, right? Interesting. Okay, how do we do it? We just call it ddx, no problem. Then as mentioned, we did create u square. Okay, no problem with that. But we can refer to this by this to the du. Then we have u square, no problem. Then du by x, right? As mentioned from this law. So we have du and du common here. Now we can easily solve the problem, can't we? we have these two, right? We just added them. Now we can easily do this for this. As you can see, we have u here, so we can just use 2u to the power 2 minus 1, which is 2u, and then du by dx. Interestingly, we know u equal to 2x square plus 8, right? So that again belongs to the law. What it is, that is dx 2x square plus 8, right? So how do we solve it? That is, we have to apply ddx on these two, both of them. As you also know that when we apply this thing, we can easily, I believe we will understand right now, that is, we will have 2, first of all, as it is constant, 2, then x squared, so it will be x, because 2 minus 1. Then for this, ddx of 8 will be 0, because it's a constant, as we have learned from the first law, and therefore here we have 2u something. So okay, a lot of things basically. Okay, so we have 2u, then 2x, right? So we have for what is the value of u? We have 2x square plus 8 into obviously x, so it should be 4 into 2x cube plus 8x, right? So it is 8x3, okay, 32x. Interesting. Did we make any mistake? 2 here. Oh, my bad again. It should have been 2 obviously, and we had x square. That means 2 will be here and then x, right? Okay, we haven't multiplied that. Okay, that's the issue we had. Okay, we'll do that. I'm just solving the problem. Simple C, but yeah. Okay, great. So how are we going to solve this issue, which should have been 2u, and it should have been obviously 2 as constant, and then we have to consider these as this 2 into x, 2 minus 1, okay, plus ddx of 8 is 0. That's it. So we have to provide the value of u again, which is 2x square plus 8, and here we have 4x that returns as, okay, for 8x to x square plus 8, which we have as 16x cube plus 64x. Great, yeah, done. Now talking about power rule on a function chain. Interesting. So when we have ddx of u to the power n, what do we have? We have n, obviously the power n, then u to the power n minus 1, then again du by dx. Okay, this is actually same as the earlier one. Same. How can we say that? Okay, assume d by dx, we have u to the power n, right? So do we have x and u same? We don't have that, right? We don't have the same. X and u are not the same. So what we can do is we can write it d by du u to the power n, and then we can write d, obviously du by dx, right? Great. And then if we just do this one, we have learned that like whatever we have, like if we have ddx of x to the power n, we can write it like n x to the power n minus 1. So here we can write just n will be here constant and u to the power n minus 1. This is done, and then du by dx. Simple as that. And the math is basically for practice. You can just pause this one and check the practice, no problem with that. So yeah, that's how it came up. So simple as that. This is the thing, and we have a practice for you. You can just practice, have an exercise from here. Okay, the interesting point starts from this one, which is called automatic differentiation. for which we have to go for the coding part. Okay, so as we have seen that dy by dx can be written as dy by du and du by dx, as they can easily cut them up. So we can just dy by dx, we can just use them for automatic differentiation. So what is that? So automatic differentiation is a concept where the application, which is basically the application of chain rule. We have seen chain rule earlier, right? So to sequence of arithmetic operations, application of chain rule to sequence forward pass of arithmetic operations. So we'll see that how things do work. Whereas chain rule by hand typically begins at most nested functions, auto differentiation basically proceeds from outermost function inward. Okay, and a small constant factor more compute than forward pass at most. Okay, so let's just learn about what forward mode or automatic differentiation is. So it basically computes gradient, okay, alongside the forward pass, okay, and best for functions with few inputs. And in general, example frameworks are JAX, STAN, and so on. Okay, so why do we need that? It's important. If we look into here, okay, if we look into here, we have previously learned y equal mx plus c, or we can call it y equal mx plus b, whatever you call it, no problem with that. Okay, this can be actually written something like that, which is like this: x, we have an arrow, m, we have an arrow, and here we are multiplying, so we are just meaning that okay, there's an x which has an arrow, and m has an arrow, and referring to multiplication. And then once we have the result of these, assume this as x, some sort of like if you have followed my linear algebra, once we have seen x equal to some sort of obviously a matrix we do have, and for m we do have some sort of matrix or constant we can have, no problem. We can multiply constant with x, we can multiply matrix with matrix, no problem with that. We can have something like that, and once we multiply them we have some sort of output, right? Okay, then what we do is we use the same matrix and we then add that matrix with b, and then we get y. This is basically a forward pass. That means you can see they are multiplying and forgetting and forwarded. Okay, forwarded, the values are forwarded. So write it like that, multiplied, then we have got this and we have got the value, and we just use this and we got y, right? And here this can be referred to as directly acyclic graph. You can see it's not it's like directly directed, and it's an acyclic graph, it's not cyclic, right? Okay, great. So what happens in machine learning is as we have seen earlier, we do have some sort of x, okay, and somehow we do get like in general what happens is we do randomly actually guess the value of m, b, and others. Okay, we do randomly actually guess them. Okay, assume that somehow the value of m should have been 3, but we guessed m as 1. Okay, we've guessed m equal to 1, no problem, and we multiplied with this matrix, then pass this with this, and just b should have been 3, but we have assumed b as 0, for example. Okay, we have just passed this and we have got some sort of y in general. Okay, now let's just assume that. Okay, now assume y has the value of 3. Okay, somehow we have got something, we have got y equal to 3. Okay, but if we would have guessed m equal to 3 and b equal 3, maybe no, or assume that the value of y should have been 9. Okay, assume that. Now you can see we have y hat and y. Right, interesting, right? The interesting part of this is there is some concept, some sort of concept which is called cost function. Now I have talked about it earlier, right? You have seen the cost is reducing. So what we do is we have some sort of cost function which is here. There are two types of cost function in general we do use in machine learning. So we will use that, and there what it will do is somehow like this process which will they actually minus them, the 3 minus 9 whatever it is, it will do that and it will get some value. For example, it is here 6 minus 6, right? But just understand what our goal is. We randomly selected m equal to 1, b equal to 0, but actually the value was 3 and b equal to 3. We didn't pick that. Actually the value of y should have been 9, but we have y hat. That means that is the one which we have got from the random choose. So 3. So our goal is 9, right? Won't it be great if the value of y hat is again 9? If that happens, the y hat minus y should be 0, right? Isn't it what we are looking for? It is minus 6, right? So the goal is to get to the point of 0. Isn't this what we learned earlier from this graph? Something like that. We're looking for the point where m is equal to 0. So we can use differentiation on this cost function to get this, and that is where the application of machine learning is. Okay, so if you just look into here, you can see the cost was 0.541. It reduced to 0.024. So okay, that is how we just work on it. This is how we work on it. So this was a forward pass basically. Okay, and we got some y hat, and you can just call it like, okay, this is y hat, and c, this is our cost function. So we can get the cost function, we can call it something like this. This is a function. Now what we do in machine learning is, then what we do is we compare the y hat with true y. As I mentioned in the previous one, we had y which was a real y, and we have y hat which is something we guessed, and then we do compare them and get the cost c. Then what we do, again use chain rule to calculate the gradient of c. As I mentioned, now we have some sort of cost. We use chain rule. That means to get the see whatever I call it. It depends on the basically how much change it is or whatever it is, or basically, right? So ddx of say whatever right now we can call it. So we are basically using the differentiation, chain rule and others to get the value. Okay, we then modify the m and b basically. Okay, why? Because like the cost was maybe, for example, some sort of, in some way we will know later on like how this cost functions to look like, but assume that our goal of y is 9 and we got y hat as 3. So somehow if you just do minus them, we get 6, right? So our goal is to get, obviously y hat is equal to, we want to get y hat equal to 9 as well, right? Then the goal is basically the difference, we want y minus y hat which is 6, we want from this to y minus y hat as 0, right? So we use differentiation basically and minimize, and then we then adjust the value of m and b. We use differentiation. I will see that. If you just look into the code, I will just show you, and then you will see the change of m and b. And then we apply this again, we get some sort of value for y hat again, we then get the c, the value of cost again, maybe from 6 to 4, then again follow the process from 4 to 2, then follow the process and get 0. This is how we do it, and then we guess it easily. So we do this, we basically follow this process. Okay, we will learn about this much more in depth, right? Okay, so this is how we are going to learn the forward passing for sure. Then partial derivatives, that's important. For basically just look into this one. Okay, great. So for partial derivatives, just like before, earlier we were basically referring to differentiation by dx of z or ddx of y or something like that, right? Sometimes it can happen that we have to differentiate based on multiple variables. Okay, so what's that meaning? That's the point. So this is what we can do. For example, here you can see we have dz by dx, right? And we gain from dz. What do we get? We do some sort of steps, right? So here, if we just look into, okay, so for this one, for z equal to x minus y square, if you go to whatever GeoGebra or Desmos, you can then actually get the graph for z equal to x square minus y square. So it will be some sort of graph. Okay, now the thing is, we might need to get get slope for both the axes. So for example, let's go to GeoGebra and check this out. Check this graph. Let me just go there and 3.3 and 3D. Okay, here it is. So if you just write z equal to x square minus y square. Great. So that is the graph for x square z equal to x square. So you can check this various ways, right? So this is x, z axis, and we have to just drag this graph and we can check this out. Let me just it again. Okay, let me remove that and again to it. Z equal x square minus y square. Okay, move this one. I believe can we reach this still? So I don't need to do that. Let's change the color to green, and maybe we have some issues with the server. We just reload this and this as input. So just to be sure, so when e is equal to x square only, so here you can see this is x, right? This is our z axis. Okay, so this is the graph we do have. Okay, and if we just try to check this out properly, whatever it is, so this is a z axis and this is our x axis. So this is actually graph we do have, and once we add minus square and enter, this is what is generated. Now what happens is this is how we can look into here. So this was basically earlier only we had one of the kind of graph, but right now we have two. Okay, so we have x square minus y square. So let me use sort of this one. Okay, so now if we try to look into the graph. This is y, right? If we take this, so x-axis, so if we have this x here, we have to drag this a bit, but the thing is, why this is zooming, we have to, yes, that's the one I was looking for. Okay, at last. Okay, so here again, so z x weight sum, and for y and it we will have another kind of one. So how can we observe that? Observe that, I believe, from the slide as well, but currently, yeah, it's getting tougher to visualize it for now. But if you just want to visualize from here as well, we can just that I wanted to show you for just another, but yeah, just look into that x, then I believe this is y, right? So, and this is like out of the screen and into this is the z-axis. So depending on that, x and z, within that we have some sort of graph. At the same time, y and z, we have some sort of graph. So as a whole, this is a combination of both of them. Okay, let me just remove that. Great. So this would be the graph actually as a whole, but yeah, I've seen this part, right? Something like that. So here x and z, we can see this, right? At the same time, for z and y, this is y, this can be y, so we have another kind of graph there. So x and y, we have that. So there in the negative part portion, we have another one. Okay, so this is how it generates. Now the point is that here we need to use kind of x, and this is z. Okay, so we can get, okay, d dx of z. Okay, we can get it like, we can find the d dx of z from here. We can get it as 2x, and should not be considered as, obviously we know how we do the ddx. How do we do it? We can go in general, the partial derivative a is represented by this, but currently let me just write it in d so that you understand. Dx of what? X is minus y square. So it will be to both, first this one, this, as x and y are not same, so just consider them as constant, and we will have 0 for this. This we will have, first of all, this 2 here, and then x2 minus 1 minus 0 is basically x. That's it. That's how we got 2x. So 2x is basically what? Any kind of, is basically slope in the points we have. Okay, so particularly in any point we have, the slope is as dz by dx equal to 2x. Now this refers to what? Like, for example, here we have x equal to 1. That means in this point of the graph, the m should be dz by dx equal to 2 into x, which is x value is 1. That means it should be what? 2, right? This is the slope. Again, we might need to look for the y-axis as well. So partial derivative actually solves this problem. It does not only solve the problem for x-axis, it will solve the problem for the y-axis as well at the same time. Okay, how can you do that? So we will learn about that, but before that, here it is. For example, for the particular one which we're looking into, this is axis and this is our z axis, and in between there is some sort of graph that generated. Okay, and we can get any we can get the slope of that using this dz by dy. Okay, sorry, and we are trying to find out like dy will actually get minus 2y only. It's only considering for the slope in between z and y axis, and this is for slope between z and x axis. That's it. But in partial derivative we will actually consider both. We'll learn that within a while. Now these are some examples for you and exercise basically, so you can solve them. Now let's look for this problem, which is a cylinder which has a length of L, right? And this is what we have. We have radius of R, no problem with that. So the volume is pi r square L. Now problem is we will just how thing works and so on. Okay, so this is no problem. So we know the volume of cylinder is pi r square L. Great problem with that. Now for example, now someone asked or someone told you like, hey, if I make any changes to the L length, basically that is something you have learned by x and y, for example. Now x considered as L and y is maybe volume. You can just consider them that. So if someone says if we make changes to the x, will that impact y? This is basically what this differentiation and or differentiation is basically, to be honest. Okay, so here it is L and y is or v. Okay, volume. So we know that dv by dv, right? dv by dl, this is what we do, and v equal to pi r square L. Okay, now we can obviously that means dl combination should be done. Okay, let me just write it here, equal to, right? Okay, d by dl pi r square. As we know, like obviously we can compute only, right? So this should be considered as a constant, so it should be pi r square, and then we have dl of L, which actually dl by dl is basically 1, which we have pi r square. Interestingly, this whole thing actually means is that when we make any change to the L, this is how the volume is impacted, which is pi r square. Okay, the volume should be like this, pi r square. Any change L results in the volume is pi r square, or in case like dl, what we can call obviously dv by dl, right? We're getting it as pi square. Means this is the change, or this is the slope. Okay, great. Now the point is not here. The point is a bit different out here. You can look into this one. When someone asks, hey, if I want to make any changes to the radius, how will that impact? This time we made change to L, right? This time if we make any changes to the R, you see the dr of v. To do that, we have what kind of stuff? We have 2 pi rl. Here you see, when we made changes to, or we did the differentiation for L, ddl of v, we got pi r square, where we didn't have any L or others. So the same thing, we didn't have the same variable. But when we are doing for actually the R, we are getting R as well, 2 pi rl. That means a change in radius by an infinite small small amount corresponds to a change in volume by 2 rl. Okay, so here dependency is out here. That's an issue. So we can obviously solve you. This is your exercise, like for a prism, you can just do the same thing. Okay, how that is impacted, or how the change in radius or change in another thing impacts, you can practice The thing is, partial derivative is important because sometimes you have to compute the stuffs. So for the partial derivatives, you see for normal derivation, differentiation, we use d, dx, or whatever it is, whatever. But for these, we just use something like this. Okay, in Bangla you may call it one, something looks like one, but not. It's something like the same thing, but it refers to partial derivatives. Okay, partial derivatives actually don't like when we write the partial derivatives, it considers the variables, variables in general, to be honest. So see the chain rule, for example, y by dx we had earlier, which we knew we just can use some sort of random d's u or whatever it is and multiply, keep it in the both of the sides, ui by du and du by dx we did earlier. But for this derivatives, partial derivatives, what we can do is du y by dx, we can just write like this, equal to same, we can write this into the same format. Okay, again for forward part we learned earlier something like that. We learned we have created something, right? Y, u, x and z something. So you see y equal to fu, right? So u is related to y, so something, and again u is related to xz variable, so you can just write that. So this basically to plan this one. Here you can see the partial derivative like ddx, so you can say that, but is the same as we earlier by du and something, and same, yes. And it helps basically y, x and z, right? So for the x, when we had x, so we had x here, and when we have z, we had it here. That's it, simple as that. So let's see how it works. Okay, when we have multiple multivariate functions, so the same thing happens. By the something, have this two and this on, we have this two. Okay, again dx, okay. Interesting, right? Here you can see that this it depends on obviously this function y is equal to, or y is dependent on u and v. Okay, again u is dependent on xz, okay, v is dependent on, okay. So then when we are differentiating y, we have to deal with both u and v, right? In general, if this was not our partial derivative, would we consider like this? That was the thing, because in general, without the general, we have y equal to something like that, y equal to f, only one variable. But in partial derivative, it can handle both. We can have multiple, it can handle multiple variables. Now due to this reason, we can see y has been has with u and v, and then u has a this, so it has a loss of connection, and it that. So in real life, partial is what that is applied, because we cannot do it manually and individually basically. So this is how it works. And talking about ui by dz, this is for u and v as well. Okay. Okay, now let's start the interesting points. So it's starting loss functions. We have talked lots of things, and let's start talking about the interesting. Okay, so gradient cost, which we were talking, right? That we have some sort of cost, and we want to reduce that within time. Okay, so if we have C, and as mentioned earlier, if you recall or check the video, I previously mentioned, depending on m and b, we do get some sort of y hat, and y hat is combined with y, and then we get c, and we use gradient, and then we get the value of m and b, and then again we do the process, we do the follow, right? Some sort of x, then we do the addition, and we get y hat, something like that. You can see we have c, we have m, we have b in different x's, right? Interesting, right? So what's the important factor? The thing is, you have to use a gradient descent to get certain points where c by dm or whatever, this one dm is the derivative is nearly 0, and dc by db is nearly 0. So earlier in our class we have seen that z equal to x square minus y square had some points, right? Obviously, so we wanted to look for its slope, and so this is almost the same thing. So our goal is to go for the least one. So let me just show you this one. So MSC. So what is MSC? So this is one of our cost functions, which we call it by mean squared error. So here you can see what's happening is we do as earlier. Okay, so we do get the y hat in, right? As mentioned, we can get y hat, no problem. Then we also have a predicted value that it should be, right? So here you can see y hat and y. We do actually get the minus of them and then square them and divide it by 1 by n, right? Divided by n. So this is the format for mean squared error. So we get this one, okay, and you can see that this is c, in general, okay. Now we haven't yet applied any sort of gradient descent here. This is c function, okay, you can call it 1. Now here c equal, you can call like you can take this as u, no problem. So we just follow the process, we will get this by d, no problem with that, and then du dy, so no problem with that. This, okay, I have got this too. Now as we have seen that this by du is this one and du by dy is this one, we've got that. Then we can again compute this one, dyi by m, okay. How? We know y equal to what? Mx plus b, I believe they have used one. So for yi, so should be something xi, mxi plus b, something. So depending on, if you just do that, you can easily see dy by dm. If you do that, dy by dm, so you can easily see that here m is considered as a constant and x xi is a constant and m dm, so it goes away, so it should be xi plus this, for this it will be 0, so it this, we got this, and again follow this process and we will get this one, okay. So this is how it is done. Okay, let me just write it in, di hat equal to mxi b, okay. Follow this process again, and if you just follow this one and differentiate, you will get xi, and just follow dy I by b, you will get 1. Now what? Now the point is, as mentioned here, here I mentioned dc by dm, we to get the least value, right? Obviously near 0, dc by db, right? So we have dc by dm, right? So now we have obviously these two common, so yeah, obviously we have created that and we have used that and we've got some sort of function. We are using basically the chain rule again, and dc by db, again we've got something. So the point, let me just clear the point. So we do have in general MB, we do guess these values to be honest. I have x matrix and we do multiply them and then we do add them, and then the y hat is generated. These are our First of all, we guess them, guess MB. Okay, then there's some real value of M and B. Using that we do get Y, and using C we know the difference between real value and the real value and one which we got, which is here. So we want to reduce that and want to get the better M and B value, and which get using dc by dB, dc by dN. That's it. That is what is done in cost functions. And once we are done and we get some good value, we will very closely end up with the real M and B value. That's it. And we'll see that. But before that, let me just show you some code. Okay, so here assume that y equal to x square plus 2. So here y equal to something like that, and this plot looks like this. This plot is in general. So if you just zoom in a bit, zoom in a bit, if you just look into that, after a while it will look like a linear. This is basically zooming in. That's it. Because basically zooming in, it seems like a linear line. No problem. Now we have talked about the limits earlier as well. So for x is minus y, x minus 1, so you can check into that. Let's just skip that for a while. I'll share these with you guys. My main point of interest is in a different thing, which is the differentiations, right? Auto difference, okay, differentiation with PyTorch, TensorFlow. Okay, we can look to that for a while. Okay, so what's that? Auto differentiation. Okay, we have value set here. That's why. Okay, assume that x equal to 5. We said that, and okay, we'll do that. But y equal to 2 is a function. Okay, no problem with that. Okay. Now dy by dx is, we know it 2x. 2 will come up here, and x should be x to the power 2 minus 1, 2x. Then the value at point x should be 2 into, obviously if x is 5, then it's 10. So we have said x equal to 5. So let's say the value x is 5. Then we say it requires grad. What does it mean? So we basically track the gradient through forward pass. So we will use the value basically 5, but after here you can see y equal to x square. This is the function we do have. Now once we are saying y dot backward, it basically does the auto differentiation. That means it computes dy by dx, which is what? Which is, for x square it should be 2x. Now if we say grad, that means provide me the dy dx value, which is this one. For this one, the value of 2x is 5, we know, so it should be 10. So it is 10. So a lot of things. It totally depends on the practice you have. Okay. Now let's go for this one. Okay. Okay, we did mention about this one. Okay. Is a tensor required grad. Yeah, just like before, if we just say value x equal to 0, y equal to 0, z equal fx y. If we just provide a forward and backward, x grade 0. Okay, that's for the function we do have. Okay, that's for the z equal to believe x square minus y square 1. You have to say that. Yes. Yes, equal to x square minus y square. So for this one particularly, you can do it individually. We know it's 2x, we know it is minus 2y, something like that. Obviously you can do that. Here you can see dz by dx is 2x and dz by dy is minus 2y, but you can do it manually, no problem with that. Interestingly, there's an interesting point, which is this: we can do it. We can set a value for this x, and we can say okay, it requires some gradient descent of y. And for y, we can set the value, and we can say. And now, interestingly, what happens is is it equal to for something. This is the function. What it does is basically creates z equal to x minus y square. Okay, and in general, the value is 0 because x and y is both 0. Then it does z dot backward, means it does the differentiation on both of the x and y. That means dz by dx and dz by dy. Now if we want to look for the for dz by dx, we can get 0 because x has the value 0, and dz dy has value minus 0 because yes, dz by dy is equal to minus 2y. Now obviously, if you couldn't understand anything right now, just stop or pause this video and check the previous portions again. And for the cylinder, the same thing is done here, so that's not very important. We have gone to integrals, that's important as well. What is important here is this one. Okay, I believe we can look in cylinder one, which can be interesting, right? Yes, cost function. Before we talk about cost function later as well. You can see, but yeah, let's talk about that. So volume is pi r square L, no problem with that. Okay, great. So what we are doing, we are just saying cylinder of should be math pi, that means pi, my r, that means r square, the same thing, pi r square. Okay, then we are saying r should have a value of r should have a value of 3. And great. Then we are again saying the L should have a value of 5, no problem, 3 and 5. Great. Then we're saying V should be V volume equal to cylinder volume of RL. R is 3, L is 5. So using 3 and 5, we will get some volume, right? Obviously, pi r square L, R, we have L, we know the value of pi, so we will get volume, no problem. Now saying, hey, we have V equal to pi r square L, we also know the value of V and so on. We're saying, hey, do some dV by both of the thing, dr and dl. That means find the differentiation basically. So dv by dr or dv by dl. So if we just look into dv by dl, which we had earlier, this one dv by dl, which is pi r square. So pi is 3.1.14 into r square. R is 3, right? 3 square is 9, 93. It's 27 up, something should be, yes, it is 28. That's it. So this L is basically referring to dv or v by dl. That's it. Now why is it important? Because understand, when we are working with the cost function, when we do the back propagation, that means just look here. Why is it important? It is because just look into here that we want to look for like somehow we have, right, no problem. Now when we call propagation, that means we do find out the basically the d by all the variables we have. So here we have dc by dm, dc by dv, okay, whatever we have. So we want it to be minimized, just nearly 0, because that should be the minimum point. That's a minimum point where which we want, because we want the least cost, because we want the least difference in y hat and y. I don't know if you are getting stuck on that, please feel free to ask in the Discord channel in our query session. I will try my best to make you understand. But yeah, I believe that's the part. Again, if you just look into dv by dl, you know pi r square, so we can just verify that is this the same thing. So we have pi, and thus we can verify they are the same thing. That means dv by dl is exactly as pi r square. Again, same for, we can just follow the same process and you can just check the other stuff. This basically shows some changes. Basically, what do you mean by dv by dl? You can see linear volume from 3 is 6, so 3 is r, l is 6, right? So have r fixed here, okay, and if we just look into here, so for r and l, r3 and l6, we have this kind of volume cylinder, and here you see if r is fixed, radius is fixed, but if you decrease the volume from 6 to 5, okay, the difference is basically 28.7. Isn't this what I told you earlier, that the difference increase or decrease in length, increase and decrease in length, which is L, it impacts on the volume is pi r, is exactly the same. This is pi r square. You can see here is a math pi r square L, pi r square, sorry. Okay, that is the thing. Again, from 7 to 6, again same thing, problem. So this is how the beauty of differentiation is, or the beauty is. So again, talking about that, dv by dr is 2 pi r l. Just follow the same process, no problem with that. Now single point regression, if I just look into these two, we'll look at that single point and batch. Let me just look into regression prior to that. Okay, this is an interesting one. Here I believe you will learn some interesting factor, the cost function. Let's look into that. A torch plot or something. Okay, we have some value x which is 0 to 7. No, okay, we have some value for 0 to 7. Okay, let's assume that. Take a paper and write them down. And we again said, like, we have some value for y, which is some sort of this. So these are the values for y. If we just plot down here for x and y, this is our values. Okay, so let me just keep it here. So I will just remove it later on. So this is for in x-axis and for y-axis. For them, these are the points, no problem with that. Now let's move to this one. Now here it is, here are the points, right? Okay. Now here you can see initialize the slope parameter the random value of 0.9. So what's that? That means, okay, these are some sort of points. If you have learned linear algebra with me, you know that we have some sort of linear line out here, right? Created that, and depending on that line, if someone says, if I want to have a dose of maybe 3.5 milliliter, how much the forgiveness score would be? Obviously we can do that from the linear, and to create the linear line, we surely need some sort of m and b, right? M is basically the slope, and the b is basically how much we should cut from y-axis. But yeah, that's the thing. So as I mentioned, that in general what happens is in differentiation calculus, we do randomly pick the value of m. I did mention that, right? We do randomly pick the value of m and b. I did mention, right? So you can see that here as well. I mentioned that we do randomly pick that and we get some sort of y hat. Like for 1 we can choose 0, and randomly we do that hat and then use the cost function to get the real one. Okay, so we can randomly pick like 0.9, for example. We can create that point, and we have randomly chosen b equal to 0.1. We can do that. Then the regression basically basically the mx plus c, basically the line. So m x plus b. So we have m, we have b, and we have values of x in out here, right here. Great, no problem. Now what? Now we just we can create the line. So it is, this one is basically created based on the random and b. Okay, if I just plot it here on top of that. So here, sorry, we have m equal to 0.9, equal 0.1. Just randomly picked them to plot to create a line. Basically, that's it. This is all. We have just randomly created this. But is this a line we're looking for? But surely not. I believe we had a line something like this, right? And it said that is the line we're looking for. In our video we have mentioned earlier, the linear algebra video, right? So that is basically this process is another solve the problem, right, rather than that linear directly. So in machine learning, what we do is we do now, as mentioned, we are just going to find the y hat as mentioned, right? Using our random m and b, we will just find the y hat problem. Then we will compare that with the real y value we should have. The real y, where is the real y? We actually have real y values, right? Here it is. Here they are. There are lots of real values. So we will compare them with this. So we'll just continue to compare them, and then this is it. Here is the thing. Here is the dc by we should d by dm and dc, sorry, dc by db, because obviously this is what we do here. And here you see m dot grad. When we say that, we basically get the value of dc by dm, okay, which is 36.30. again d dot grad, for that we get something like 6.2650. but we want to get the value as close as 0, okay, as close as like this dc by dv and by dm. So this process should be continued for a long period of time. That is the process. Now is an interesting point of gradient descent which we have, obviously. So this is basically used, this is basically done through SGD, stochastic gradient descent. So how we modify the value of m again. So modify the value of m to a new value, so that then we can try. So we had some sort of random value like 0.9 and 0. m 0.9, m had a value of 0.9 and b had a value of 0.1. now we have a new m and new b, and again follow the process and so on. So again after the process, we have a new m which is 0.539 and a b which is 0.0374. previously it was 0.9 and now it is 0.539. it has been better now. 0.539 has followed some optimization process, and for b it has followed some. Now the graph looks like that. Again, it is not the correct one, so it should be follow the same process again and again and again. And now you see the difference what's happening. So here you can see the cost is MSC is 8.5. we are doing the whole process again and again for 999, which is maybe starting from 0, right? So 1000 times. Okay, so once we do that, you can see the cost function started with 8.57. now that ended with 0.0195. so what does it mean? I'm going to obviously make sure what you want what's happening. Let me just remove this one and this one as well. So the goal is let me just verify what's happening. Okay, so the point is we have some sort of x values, a list of values 1 0 1 2 3 or something, and we have some sort of values for 1.3 1.4 or something, right? Now obviously using them we do have some sort of point, but in general we know, like if we create a linear algebra we can get some sort of line maybe in between. Obviously create a bad line, should be something like that. Using that we can get for any particular x, now then we can get particular y, no problem. But there is another using the gradient descent. What we do is we guess the value of m, we guess the value of b, just a random guess. Then we do follow the process. What we do is basically have something called c. So using m and b, then we get some sort of y hat, which is y hat is equal to m x plus c, or sorry b. So we know m, we know b, and depending on the x we have, we do some sort of y hat. But maybe assume that it is 0, sorry, assume that it's 1. Okay, it's 1, and m we have guessed 0.9, right? And b is 0.1, 9.1, it is 1, right? So but the value is 1.4, right? That means y hat value is 1, but y value is 1.4, which is not same, which is not same. So our goal is c equal to, we have 1 by n, and y I hat by y I squared. So the process, it follows the process. So get 1 minus 1 so 1 is here, minus 1.4 square, and 1 by how much value we have, we maybe have 8 or 9 values. Do that and we get some sort of cost. Now what we do then is we do get some cost, maybe 8.4, assume that we got it code, I believe 0.57. okay, then what we do is we want to look for this is not where we are happy. I believe I have mentioned that we want to look for c by dm, because it's minima point. Okay, in here maybe c and m, minima point where it should be the least value, minima. So in the least value we have minima. Okay, we have the slope as, or slope as 0. So we want to look for the minimum. We start with the gradient, and we just want to look for the dc by dm. So we want to look for a value very near to 0. So we start doing that. We start doing dc by db, why dc, because y is equal to mx plus b. So we have m and b, so we that's doing that process. X is fixed, right? So you're doing that. So we try to look for the least value. So if you just look into the code, you will see that m grad, that means it is it is dc by dm is 23, dc by db is 3.6. so everything decreases, and at a point here dc by dm it is 0.0006, that is very near to 0. Then again dc by db 0.003, that is it is very near to 0. So and the cost has been very minimized. It was earlier 8.5 and it is right now 0.0195. So it is good. And why we stopped here, why we didn't get cost equal to 0? Because you see after 996 or so, you can see it is 999, but the cost is still the same. That means it's not decreasing any longer. So that is 1000 epoch is the perfect. So if you are working in machine learning, you will see that. So the what we can say is now we have perfect m, almost the perfect b value. These are different values obviously, but we have perfect m and values we have right now, almost perfect. You can look into that here. You can see now the value we have m and b. Using that, if you plot, you can see this is almost a perfect line we have. That is the we have got. Okay, I hope you understood right now. That means using that we have got least or minimum value for m, which which basically gives us almost the same value to generate this one. Okay, so we followed the process and got the perfect c, m and b. And now as we have perfect m and b, we know the value of x. We'll just plot that, we'll have the perfect line. Then that's how we can again solve the problem. We have done it earlier using linear algebra only. Right now it's we have solved it using this one. So you can see the value of m was actually, m we have got right now is minus 0.68 and b is 1.75. That's it. So that is for the part. Okay, again, these two should be completed before the integration. Gradient of a single point of regression, exactly the same, x, y, and regression m dot b. Okay, in particular choose forward pass. We have done that. Forward pass, compare by b, we have done that. But this time obviously we have used mean error, but yeah, this should not be exactly the same. Yeah, follow the process, same thing. Gradient of cost bc. Okay, it's the same thing. Okay, again, share these links, notebook links with you guys. Video, same process, same values we have, or just different. Basically, this cost is different. That's it. So just you have seen this part only in the single point here. You can see here. Here had by y, but MSc basically this one. So MSc you can see the same, exactly the same thing we have. That's it. You can, again, interestingly, in this one, what you can do is you can visualize the game, how this plot is changing. So you can see here we have just used 8 epoch, but you know, if we use 1,000 epochs, you will exactly see the how this is changing. Now you just for an example, if you just for 8 epoch 8 times, you can see for this is when, like I mentioned, the first was 8.57, right? I mentioned that. Then we follow to follow the whole process again, did what DDAC, DC by DM, DC by DB, and so on, and we good M value, better value than this, we got this line. Okay, again, so the same process, cost is reduced, again we got some M. We follow the same process again, cost is reduced from 2.5 to 1.51, and we got some M and B, and this line we follow the same process and go on, and this is the line for 80 only. But if you change it, I will obviously code, your task is to change it and make it to 1,000. But the problem is you will have 1,000 images. It will be interesting, to be honest, to see. Right, let me just run this, to be honest, so that it runs and we have 1,000 images by the end of this. Then we'll just obviously check it, but let me again go for integral. Here we'll talk about it after once it is done. Then obviously, okay, so integral part will obviously start learning that, but yeah, learning. Okay, oh, I haven't changed that. That's the issue. Okay, let me just run, and this should take some time. And okay, let's give it some time. By that time, obviously, let's just focus on the integral. Let's go for that. Okay, we'll just look into the higher order partial derivatives. That's basically 4 powers we have. So z equal x square for x, xy to y squared, so on, of the stuff. So assume that this is z equal to something. So if you want to dz by dx for only x, you will end up with this. For dz by dy, we'll end up with this. Then higher order partial derivatives. Also look into these ones, which is dz by dx is 2x plus 5, dz by dy 5y. I've got that right from here, and I've got it from here, no problem. Now, I mean by higher order, that means if we want to get like the dz by dx of this one, you can see dz by dx of this one, means again, okay, we got it. Okay, process got 4. Basically the same thing I have mentioned, like d by t, we had some sort of graph, something, and this m referred to d something, and then again we had this maybe as dt, this call it as v, a refer to d dt, and you can V as obviously D V as D D D D. So yeah, higher order. So we're getting differentiation on top of another differentiation. So yeah, that's that part. So in a lot of ways, this is unmixed way where you can see there's a dx square. We can do that. There's another way which is called mixed way. So it was d square z dx square, but we could have done d square z by dx dy. That's a different way, which is mixed way, and sometimes if you're a beginner you might make mistakes with it. So what we do is basically, first of all, you can understand from this is easily this z by x dy. That means if we just divide it, it should be dz by dx dy. So we do it first and then we do it. Okay, we do it first. So here you see dz by dy, we do it. So we got the value and then the dx, done. Same process, d square z dy is. So it depends on how, what the requirement. So we can do that. That's the thing. That's the point. So yeah, sometimes again, like d squared by dx dy is d squared by dy dx sometimes, but not always. So there are a lot of things, obviously, and this is how we can refer to them, higher order ones, like d squared by dx square as xx, d squared z by dy dx. Here you can see it's different, both are different. So this is important, which is you can see f x y. What does it mean? What does it mean? Here you can see the x is done. Obviously dx is done first, and then dz by dy is done. So f x y, x is first and y is later. So it's almost the opposite. So these are the things. Sometimes will be asked, hey, f x y, just get the f x y, or this one or something. So it's totally for the mathematics. Just learn later on. But they're not going to be directly in our machine learning, but these are something that picks up machine learning. So here we have exercise, pause this and solve the problem. And this is interesting for integral, so let's talk about it. So actually right now we have learned we had y equal to something, right? We had some sort of value and we have predicted y, which is hat. So in machine learning, something called confusion matrix, where we create a matrix where we should find like for actual y, once we have 1 and 0, that means value should be 1, value is true positive, and that's false positive, and predicted y. We just create a matrix to understand how much correct we got our output, and so the predicted y hat is here, y is here, 1 and 0. So you can see this point, like the value we have here, we have 4 values, okay, in matrix. Let's remove this one. We have 4 values, okay. Okay, and remove this one as well. So y is here and y is here, 1 0 and 1 0. So okay, we have some values for confusion matrix, no problem with that. So the value we have here is called true positive. Whatever we should have, we have. True positive, we have. This is your total task, that what is true positive, what is positive, what is false negative, what is true negative. So this is your task. Then we have some sort of value called false positive, false negative, and true negative. To be honest, if you don't understand them, you can't solve the problem, or you can understand if your machine learning model is learning or not. Okay, so depending on these 4, we do get some of we have a matrix, okay, maybe 36 4 2 9, whatever, just for an example. We can have that. Again, this is a value we can have. Now obviously this is a confusion matrix of this, okay. This kind of things we can have. Now let's give another example. Assume that this person or this cartoon has sort of hot dog with in hand of. Now the thing, we have to detect if this is a hot dog or not. If we can detect that if it's a hot dog, we will say that y hat is 1, but then again else it should be 0. Okay, great. So from here we understand here. So here look into here saying that 0 means not a hot dog. Okay, 1 means hot dog. Great. 0 means not a hot dog, means hot dog for y. For y hat, we're getting like 0.3. We have got 0.5 for 1. Like when we should have of 0, we are actually getting a value of 0.3. Just like that. When we have a value of 1, we are actually getting some sort of value like 0.5. When we should have a value of 0, that's not a hot dog. Like I have hot dog, something, and not hot dog. Okay. So when someone is showing me this not a hot dog, the y hat is okay, the value should be 0.3. Actually, it should be 0. That means it should be value 0 to indicate the part that hey, it's not a hot dog, but it is not still 0. Okay, when okay, again it should not be a hot dog, it is saying 6, which is bad. Again, it is a hot dog, it's showing a hot dog. It should be 1, but it is predicting that it is 0.9. That means okay, very near. That's good. So these are our predictions. Okay, our predictions. These values do let them know, let the model know, let the person know, like if we are able to decide or if we are able to judge the actual image or hot dog. 0.3 need to 0. Okay, it should be good. 0.5 not good. Like obviously it's a medium of 1, but not good. 0.64, it should have been 0, but it's very bad. And 0.9. So now if we say like okay, we have a threshold of 0.3, that means if we have bigger than 0.3, we are we have a threshold value of 0.3. okay, what I mean, that means we can have 0.3 no problem. Okay, and if we have 0.3, we can refer to 0, no problem. And if we have a value bigger than 0.3, we can consider that as 1, not 0. Means 0.3 if 0 and bigger than 0.3 is referred to 1. Okay, so it is 1, and 0.6, which is bigger to 0.3, is to 1. So it should have been 0, right? But it is we have followed a process and now it is 1, and 0. Obviously bigger than. So that means if you see the format and if you just compare them, you see 0 1 1 1 0 1 0 1. Here's a mistake, right? And if you did the threshold to 0.5, follow the process, you see there are 2 mistakes. If you follow the threshold of 0.6, you can get 1 mistake. Okay, there is another thing called true positive. Then using these things, all of the values, how much we have, we can count them, and false positive rate, we can count how much positive we do have, true positive and false positive, we do get some sort of values, right? We can get them. Not only for this, but we are just getting all of them, right? You can see for 0 threshold we are getting 1 and 0. True positive, and false positive. For threshold we are getting this value. For this threshold we are getting these values. Okay, now the interesting part comes up. Using these points like 1 0, if we have false positive fp, this one, and we have true positive here, so we just plot them 1 0 false positive. If we have false positive and we have false positive is 0.55 and we have 1, so here is the 1 for this one, 0. 0.5, obviously it should be here, obviously here, and here we have 0.5, 0.5, this one. So these are the points we do have. We have this one. Okay, wait, we have false positive rate 0.51. Okay, this. Okay, we have these 3 points, and these are the points we have. Now our goal is to get the area here, because the more area we cover, the more better model is. If it covers the whole one, if it would have covered like instead of 0 like this one 0.5, if it was actually 1, it would have covered this one. Means the model would cover the whole square, and it would have been what we're looking for. Actually, it would have the perfect model. Okay, but here we can see almost 25% is covered, and yeah, this is basically what we call ROC curve, and the perfect one is basically which covers the whole square. The random one which covers this portion, the above chance is this one. For the good it is something. So we have a good, but we have talked about it visually, right? Haven't talked about it mathematically. So we can actually do that. In general, what happens, I mentioned, you have seen the circle we had, although it's not a circle, but we had a circle in example earlier. So you have seen, I mean, if we increase the line, we can cover the whole circle just like that. If we have some sort of lines, and if you get the area of it, we have dx. Okay, great. If we decrease dx, there are much more rectangles we have, you can see. But if we have dx of one line, we can cover the whole one, means this dx. So by now you have learned dx, ddx or something. These are meaning very small portion. The del x, dx are the same, but yeah, if we just increase the value of decrease value, then it can cover the whole area. So integral is basically like that. So integral is what? It is basically the opposite of differentiation. Differentiation basically divides and divides and divides. Integration basically adds and adds up. Okay, so how we do is we basically have some sort of sign like integration. This is here we put some sort of function y equal to 2x or whatever it is, and we mention in which axis we are going to add. We basically going to sum up and whatever it is, basically meaning the x-axis. Okay, so let's understand. There are some laws we have. So integration of dx to the dx, which is basically x to the power n plus 1 by n plus 1 plus c, a lot of things basically. The laws we have, and for example, this is example x to the power 4 or 5 by 5. Okay, again, if you have multiple functions and if we integrate them, and we can with these things, and if we have some sort of constant, we just put the constant outside and then do the integration. The example is this. We have 9, so we put this here and we choose this one. That's it. And you have another exercise here. This is the exercise for you. Now let's look into an example of how definite integrals work. So for example, this is a y-axis and x-axis, and in x1 x2 point we want to get the area here. So what we do is we have x1 and x2, no problem with that, and we basically get this x1 and we just use in x1 x2. Okay, right. Now the point is for this one, if we y equal to half x, this is the line we have, that is m equal to half, that means 0.5, no problem. And if you want to get the area between 1 and 2, we have to set 1 and 2, half x, then this y equal to half x, and this is basically dealing with the x-axis, with the x-axis basically, right? 1 to 2, so dx, we write dx. This we've solved the integration and value. Okay, actually like this, if we just follow this one and just get the whole value actually again. This is for x equal to 1. Obviously this should cover this one only, x to 1 and 2. Obviously x equal to 1 value is this, x equal to 2 value is this, and I have to do some sort of minus here. I believe let me just go here. Okay, so yeah, yes, that's one. So if you just look into here 1 and 2, so for x equal to 1 equal to 2 we have got the values, no problem. What we do is we just do for x equal to 1 what's the value, right, and x equal to 2 we got the value. So for x equal to 2, whatever, for x equal to whatever the value we have, for x equal to 1 whatever the value we have, just do the minus and we get the area we have here in this point. Okay, that's it. Now again we have another example in test which is for integral for 4, and we have 2x and dx. Just easily follow the process. 2 will be in constant here, then you do the integration, done problem, then find the value for 3, find the value for 4, then minus the value for x equal to 4 and x equal to 3, minus them, then we got the value. So this is again actually indicates some area. So this is needed to calculate this one. Okay, now we have this one, as we have learned earlier, these points are here, and in integration we'll just look into that, these are the points that are in our code. You will see 0, 0, 0.5, 0.5, okay, 0, 0, okay, 0, 0.5, 0, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5 and 1, 0.5 and 1, 1, right, whole one. Okay, points we have. So if we do that, there is a function basically which we can use here. Okay, we can call AUC and then actually mention the point. You can get 0.75, which is 75%, which actually what we guessed, right? Almost 75% was covered. So yeah, that's the thing. So we can call like, okay, that's a very good model, but if it increases, basically we haven't learned how to calculate the integration. Rather, there is already built-in one which use this formula. So this is what we learn. We learn some basic of integration, probabilities. But before that, let's just look into here. Let me see if we have 1000. I believe if you just you can see it's lots of images. If you just into that, and if you just go, you can see it's changing. Okay, let me just start from here. Okay, so start from here. It was here. Okay, from here to here. Then let me just take it to here. You can see it is changing, and it's changing, and 1000. So you have to reach 1001, and you can see now almost we have reached, and here you can see the perfect line we have. Okay, you can see the cost is not decreasing much, 0.0227, 0.0227, 0.228. So yeah, this is the line. So this is how the line has changed depending on the gradient descent we have. That's it, right? Interesting. Now let's talk about some sort of probability. So you can just check out this notebook as well, no problem with that. But there's some easy concepts, like I believe if you have learned the basic probabilities, it will be much easier. But there are lot more concepts out there, so I will share other resources in the comment section as well, as we are ending our mathematics for machine learning series. So we'll see that, but let's assume that there is a coin flip. Okay, a coin has basically head and tail. So the chance of getting a head is basically because there is one head and 2 is basically meaning head and tail both. So we have two options and head has one option. 1 by 2 is half. Tail is only one option for tail, and we have total 2. That means in the option we have, we will put it here, and how many sample space or how many options we do have in general, we will add that here. So this is how we get basically the probability of something, like probability of head, probability of tail. Okay, that's not the point. The point is different. That is like this. A lot of obviously probability theories and others you learn. They'll obviously dependency theories, but yeah, we might not be able to cover that here. Okay, ace of spades. So this is only the one we have, ace of spades. So why did we show this to you? That is because it's saying what's the probability of getting ace of spades. As we like in, if you have played basically cards game, so you might have heard about it. It's actually 52 cards. So ace of spades is only one. So we have in total 52 cards, obviously, as mentioned, all of those we have. And ace of spades, we have how many ace of spades? Only one. So the probability of getting ace of spades is 0.019. Again, ace of spades is only one, but there are 4 aces. So here, if you just look to here, so 4 kinds of cards. So you see all of these are ace. So see, so we have 4 options. So 4 52, because the question is the chance of getting ace only. So ace can be of different type, right? So we have 4 options, so 4. So some we can look into other things as well. Again, okay, let's look into this one. Assume that we have 2 coins. Okay, so if we have 2 coins, obviously coins, each coin has head and a tail, so it says the probability of getting 2 consecutive head. What does it mean? It means the first coin will have a head, the second coin will also have a head. Okay, let me just write this down. That means we have a coin, it can have head or tail. It can have head or tail. It can have head or tail, no problem. So okay, what options we do have? Let me just write. We can have head, tail, head, tail, tail, head, tail, tail, one time tail. Okay, 2 tail, 1 time head, 2 head. Okay, these are the options we have. 4. Right. We have more options. I don't think so. All of the options we have is 4, and we can see the head is 4 times. We can have head 2 times. Okay, consecutively it will have a head. It will have a head. A 2h. Obviously, it is only one type. So it is 1. 1 by 4 is 0.25. And again for 3 head, so 3 coins. If you want to look for 3, if you want to have 3 consecutive heads, this is what we should have. What? 3 coins, you can see this is the option we have. We have head, tail, head, and so on. So we have 8 in general. So how do you understand? As you know, we have 2 options, head and tail, 2, and we have 3. So 2 to the power 3, which is 8. We have in general, you can see count, we have options. Our question is how many, what is the probability of getting 3 heads? Okay, so obviously we can have heads for 1 time, and we have all of the options as we have total options 8. So yeah, it should be 1 by 8, right? 1 by 8, right? Great. Problem again, there's something like combining probabilities. So if someone asks, hey, how's the probability of getting 5 heads, you can just divide it by probability of getting 2 head, getting 3 head consecutively get that. Okay, there's another concept, combinatorics, which is basically choosing. It's basically concept of choosing. Assume that is basically called NCK or something like that, which we represent by these brackets. We'll talk about that, but example, there's a question, a solution provided here. This is totally you can look into, obviously. Let me just look into this one example. Okay, assume you have 3 coins, and if you're interested in a number of ways to get 2 head flips, just understand what's happening. We have 3 coins, right? Our goal is to get we are interested in the number of ways to get 2 heads. Mane, the theory is in how many ways to get only 2 heads. Okay, let's just look into here. Okay, so you can see 2 heads, 1 2 1 2 1. So we have these 2 heads only for 3 times, right? So this has been asked. We have 3 coins, so we have asked number of ways we can have only 2 heads. It is in general we can see. So you call, okay, this should be 3, but there is another way to actually do it mathematically, which is called 3C2, which is we have 3 coin. Is it good if we just have like 3 coins? Obviously we'll be happy obviously if 2 of the coins have head, right? That means we just want to 2 coins and we want to have head out there. So this is the combination which is called choosing, something like that. Like from 3 coins we just want to choose from 3 coins we want to choose 2 coins where we want to maybe have some sort of head or whatever it is. So it is 3. Again, the same question can be asked for the 2 tails, right? From 3 coins we just choose 2 coins to tail on them, right? Again, from if you want to have tail, so what we can, from 3 tail we want every single coin to have tail on them. Okay, so it should be from 3 we have to choose obviously all of the coin to have, right? Or we have to choose all of the coin to have tail, then it should be dt. So from 3 we have to choose 3, which should be 3C3. So this is a concept which is combinatorics. Just obviously I know I have been through all of these stuffs, the later parts, but I will be providing the resource so you can learn. Okay, so just follow the description section or the comment section. You will get those links there. Okay, you can learn depth. So this is basically NC. Okay, from n number of things we want to choose k number of things. So this is what we can do. So this is a problem you can just practice. This problem is basically the same as this one, and this one is pretty much this might be very challenging for you, but this is in NCK. This is what we have learned just a moment back, and yeah, that's it. And yeah, that should be enough. And we have the notebook is back obviously, but all of the topics are not going to be covered, but the basic ones for the combinatorics and some sort of probability cover that. Okay, and the probability range should be in between 0 to 1. Okay, not on that or not bigger than 1. So yeah, thank you so much for watching this video, and that will be the end of our mathematics for machine learning. Now in the next week we'll learn about data pre-processing and feature engineering. Okay, thank you so much and hope to see you next video.